Welcome to our podcast, Artificial Intelligence, Papers and Concepts. I am Jack Malik, your AI-generated host, and with me is my AI-generated co-host, Sophia Lane. We sort through the noise to find the signals, the really important stuff. Today we're getting into something pretty cool. Vision language models, VLMs. Mm-hmm. These AIs, they understand pictures and words. It's opening up totally new ways to interact with tech, but there's a catch.
Right, there usually is.
These things are often huge, massive. They need tons of computing power. Like, think of a supercar needing its own private racetrack just to get going.
Exactly, and that's the wall SmolVLM is built to get around. It's this new family of models designed specifically to be, well, small but really powerful, kind of redefining efficient AI.
Small but mighty. I like that. So our mission today is to dig into the details. How do they do it? What are the specific design choices? The surprising results from the research that let SmolVLM perform so well but stay so small, making this advanced stuff accessible on everyday devices.
Yeah, and for this deep dive, we're mainly looking at their research paper, SmolVLM, Redefining Small and Efficient Multimodal Models. There's also a great HuggingFace blog post that adds some context. Together, they give us the full picture.
Okay, let's get into it. We know large VLMs are impressive. IDFIX, 80B, 80 billion parameters, performs amazingly. Mm-hmm. But like you said, they need serious hardware.
Right. Not exactly phone-friendly.
Definitely not. And it sounds like just shrinking the big models wasn't the answer either.
No, not really. That was the initial problem. A lot of the early, smaller VLMs just copied the big guys' homework, so to speak. They used things like extensive image tokenization, which sounds good, but it ended up being super inefficient with GPU memory.
Ah, counterintuitive.
Totally. It made them impractical for running actually on a device. So yeah, there was this big gap, and that's where SmolVLM comes in.
So they didn't just shrink, they rethought it.
Completely. That's the really interesting part. SmolVLM wasn't just scaled down. It was engineered from square one for efficiency. They looked at everything, the architecture, how images are turned into tokens, the data they train on, all optimized for low compute cost. That was the core idea.
Sounds painstaking.
Yeah.
Do you walk us through some of those key decisions? What did they actually change?
Sure. So one big thing was figuring out the balance. A VLM has, a vision part, the encoder that makes vision tokens from an image, and a language part, the LM that understands them.
Right.
They found that for compact models, you really need a good balance between the size of the encoder and the LM. And surprisingly, smaller vision encoders often turned out to be better for overall efficiency.
Huh. So a bigger eye wasn't always helpful. How did that show up in testing?
Well, for example, they tried pairing a big vision encoder, like 428 million parameters, with their smallest language model, only 135 million. Yeah. And performance actually went down. Yeah, it showed the balance was off. Now, a slightly bigger LM, 360 million params, did get a boost from the big encoder, about 11.6% better performance, but that came with a 66% jump in total parameters. So the smaller encoder was still way more efficient.
Okay.
It was only when they got to their biggest LM, 1.7 billion parameters, that the big encoder really paid off, adding just 10% more parameters for a good performance jump. So it's all about matching the pieces smartly.
That makes total sense. What about handling bigger images or, lots of information? That always seems like a bottleneck.
It really is. A standard 512 by 512 image, that alone can become like 124 tokens.
Right.
And lots of smaller LMs choke after maybe 2,000 tokens. So SmolVLM tackled this. They boosted the ROP base, that's a technique for handling longer sequences, way up from 10K to 273K. And they specifically fine-tuned on long context data.
Oh, okay.
And the finding was pretty clear. Compact VLMs get a huge benefit from longer context windows. Their biggest model could handle 16K tokens, the smaller ones up to 8K.
That's pretty impressive for small models.
Yeah.
Any other tricks for handling the visual side efficiently?
Yeah, they got quite aggressive with something called pixel shuffle.
Pixel shuffle?
Yeah, basically you rearrange the spatial information in an image into more channels. It reduces the spatial size, the number of tokens, but packs more info into each one.
Okay, denser information.
Exactly. Now, bigger models might use a shuffle ratio of 2, cutting tokens by 4 times. SmolVLM found that for their small models, a ratio of 4, a 16x reduction worked better.
16 times fewer tokens.
Yep. That massively reduced the attention overhead, basically, how much work the model does looking at all the tokens and help with those longer contexts we just talked about. They did have to tweak their vision backbone slightly, using 384 by 384 patches instead of the usual 364 by 364 to make it work well.
Clever. So seeing smarter, not just less. How did they apply this efficiency idea to high-res images or even video?
Good question. For high-res images, they used an image splitting strategy. They'd break the image into smaller chunks, plus include a smaller version of the whole thing. Keeps the detail without killing the compute budget, kind of like what YouReader does.
Okay, makes sense.
Oops.
And video. That seems even harder.
It is.
Yeah.
And here's another interesting finding. They tested common video techniques like averaging frames together.
Yeah.
And for these small models, it actually hurt performance.
Really?
Yeah, so they just ditched frame averaging entirely for SmolVLM. They simply rescale the frames. It shows how you really have to tailor the approach specifically for compact models, not just assume what works for big ones will scale down.
That's a great point. Okay, so the architecture is smart. What about the training? How do you teach a small model effectively?
Right, the small instruction tuning. This had its own set of challenges and clever solutions. One early problem was just telling the model where the different parts of a split image were.
Ah, the positioning.
Exactly. They first tried simple text, like, row 1, col 2. But that caused this weird issue they called the OCR loss plague.
OCR loss plague. Sounds bad.
It was. The model's training loss would suddenly drop, but performance wouldn't improve. It seemed like it was struggling to reliably read text or understand layouts and documents. Very unstable.
So how did they fix the plague?
They switched to using learned positional tokens. Instead of fixed text, these are tokens the model learns to associate with positions, and that worked much better. Training was more stable, convergence was faster, and OCR accuracy shot up, especially for the smaller models. So, the takeaway, learned positional tokens are way better than raw text ones for these compact VLMs.
Okay, so even communicating position needs to be learned. Did they structure the prompts differently too?
They did. Clear communication was key. They used system prompts, telling the model its role, like, you are a useful conversational assistant. And they added special media intro-outro tokens. Things like, here is an image, or here are end frames sampled from a video, just clearly marking where the visual stuff begins and ends.
Makes sense.
And the finding was clear. These structured prompts and media tokens really boosted performance, especially for video tasks where the model might get confused about different frames or images.
Okay. And I know masking is a technique used in training sometimes. Did they use that?
Yep. They found that masking user prompts during the fine-tuning phase helped. Meaning the model only gets trained on generating the answer or completion, not on the user's question itself. This helps reduce overfitting, especially on tasks like question answering where the questions might be kind of repetitive. Forces it to understand, not just memorize pairs.
Got it. Now here's something that seems backward to me. Wouldn't you want to reuse all that good text data from training big language models?
More data equals better, right? You'd think so. But this was one of their most counterintuitive findings. Adding extra text data from a standard supervised fine-tuning blend they called theirs, Smalltalk, actually hurt the performance of these smaller multimodal models.
Hurt it. How much?
By up to 3.7% on video tasks and even 6.5% on image tasks.
Whoa. Why?
They think it reduced the diversity of the data. It sort of drowned out the important multimodal signals, maybe. It really challenges that more data is always better idea. For these compact models, the balance of data types seems crucial. They ended up sticking to a strict 14% text proportion in their training mix.
Fascinating. Less, or at least different, is more sometimes.
Okay, what about chain of thought? CoT, showing the model reasoning steps that helps big models reason better, right?
It does, yeah, for the big ones. But again, different story for the small ones. They found that too much CoT data actually harmed performance.
Harmed it, yep. While large models thrive on lots of CoT examples, SmolVLM did best with just a tiny fraction, like 0.02% to 0.05% of the data being CoT. Any more than that seemed to, quote, overwhelm the limited capacity of the smaller models, making them worse at the visual stuff.
So you have to be really careful not to overload them, even with reasoning examples. Okay, last training question. Video length. Did that matter?
It did. They found a sweet spot. Moderately increasing the video duration during training actually helped performance on both video and image tasks.
Interesting. How long?
Performance improved as the videos got closer to about 3.5 minutes long. After that, the compute costs started to outweigh the benefits, diminishing returns.
Right. Wow, okay. That's a ton of really specific, careful tuning. It sounds impressive, but the results. Do these small models actually hold up against the competition in the real world?
That's the million-dollar question, right? And the numbers are pretty compelling. So they have 3 main versions. SmolVLM 256M, that's a tiny one, uses less than a gigabyte of GPU memory.
Less than 1 GB. Seriously.
Yeah. Seriously. 0.8 GB for single image inference, ideal for really tight resource constraints like basic edge devices. Then there's a middle one, SmolVLM 500M, uses about 1.2 GB, good balance. And the biggest one, SmolVLM 2.2B, needs about 4.9 GB of GPU memory aimed at higher-end edge systems.
Okay, 0.8 GB is just wild for a VLM. But can that tiny one actually perform? How does it compare to, say, that giant IDFix model you mentioned?
Okay, get this. The SmolVLM 256M, the tiny one, it actually outperforms the IDFix 80B model, which is 300 times larger.
Wait, outperforms the 80 billion parameter one?
Outperforms it. And there was an 18-month gap in development time, too, favoring IDFix. It's kind of stunning.
That is stunning. And the memory usage comparison.
It really highlights the point. SmolVLM 2.2B uses 4.9 GB VRM. Compare that to others in the similar parameter range. Qwen2 VL2B needs 13.7 GB, Intern VL2B needs 10.5 GB, and a bigger model like Malmo AA1B7B, a whopping 27.7 GB. It just hammers home that parameter count isn't the whole story for VLMs. RAM usage tells you a lot more about the real-world compute cost.
So they're lean on memory? Yeah. Are they fast, too? Does that efficiency translate?
Big time. Because the memory footprint is so small, computation is faster. Their tests showed prefill throughput, that's like processing the initial prompt, is 3.3 to 4.5 times faster than Qwen2 VL, and generating the response 7.5 to 16 times faster.
Whoa, 16 times faster generation. That's huge for usability.
Absolutely. Makes them feel really responsive.
What about video? You said they ditched frame averaging. Can they still understand video well?
Remarkably well, considering their size. The SmolVLM 2.2B model, for instance, does great on benchmarks like Video MME and WorldSense, even beating much larger models sometimes. On another benchmark, Cinepile, it scores 27.14%, putting it right between Intern VL2 2B and Video Lava 7B. That shows pretty sophisticated understanding of what's happening over time. Looking at examples, they show, great scene understanding and object recognition, maybe just a few minor hiccups with really complex temporal stuff, but still, very impressive for the size.
This really does feel like a shift. Okay, so the performance is there. What does this mean for, us, for the listeners? Can I actually run this thing on my laptop?
That's the really exciting part, practicality. That smallest 256M version, they got it running locally inside a web browser using WebGPU.
In a browser.
Yep. And on a 14-inch MacBook Pro with an M4 Max chip, it was hitting up to 80 decode tokens per second.
80 tokens per second?
Yeah.
On a laptop. In a browser. That's incredible. That changes everything in terms of who can access and use this kind of AI. It's not just in massive data centers anymore.
Exactly. It's a huge step for democratization, and they're leaning into that. Everything is open source, the model weights, the data sets they compiled, the training code. They even have a demo mobile app, Hugging Snap, showing it running on a smartphone.
That level of openness is fantastic. Are people already starting to build things with SmolVLM?
They are. A few examples mentioned are SmolVLM, which is specifically focused on running the stuff efficiently on mobile devices and regular laptops. Then there's SmolDockling. That's an ultra-compact 256M version, fine-tuned for document understanding and conversion, using something called doc tags. Think really efficient document processing.
Okay.
And perhaps most impactfully, BioVQA. That's using SmolVLM for biomedical visual question answering, helping doctors interpret medical images quickly and reliably right where they might need it, even if they don't have high-end computing resources available.
Wow, from general use to highly specialized critical applications like healthcare. That's quite a range. This has been really eye-opening. SmolVLM definitely feels like more than just another model release. It's a leap in making powerful AI, this multimodal stuff, truly accessible. Getting state-of-the-art results in a package small enough for our own devices, it just lowers the barrier so dramatically.
It really does. And what's so fascinating, I think, is how it shifts our whole idea of what powerful AI even means. It's not just about being the biggest anymore.
Right.
Which leads to a pretty interesting question, doesn't it? If smart design and a focus on efficiency can give us this kind of performance and accessibility, well, what kinds of edge AI applications, things we thought were maybe years away, could actually become reality much, much sooner than we thought?
All right, that is all we wanted to cover in today's podcast. Please subscribe to our channel to get regular episodes on AI papers and concepts. See you in our next episode.